Okay, so what I want to talk about now is probably the most important distribution that you're likely to encounter in engineering applications, and probably the one that you've heard the most about in the context of just like pop science, right? So this Gaussian distribution is also known as the bell curve or the normal distribution. And the Gaussian distribution has this familiar shape of something that's symmetric around some average value, which we call mu, or the mean. And then there's also this other parameter, sigma, called the standard deviation, that kind of characterizes how peaked together things are around the mean. And sometimes we call sigma squared the variance of the distribution. And so this comes up all the time when you're doing things like you take the histogram of the heights of students in a class and it looks like a bell curve, or you take the histogram of test scores on some standardized exam. Or in electrical engineering applications, oftentimes it comes up in the context of the noise that you see in some system, right? So measurement noise from a sensor or communication noise coming through a channel. And even if your noise isn't actually Gaussian, it turns out that if you average lots and lots of any kind of noise, eventually it turns into a Gaussian distribution. We're going to talk about that in several lectures. That's called the central limit theorem, which is really important. So let me just give you some intuition for the sigma parameters. So when sigma is small, that means that things are really peaked pretty sharply around the mean. And when sigma is large, then things are a little bit more spread out. And so to understand why this happens, we have to write down the functional form of the PDF, which is a little bit complicated. And as we'll talk about, unfortunately, it's not so easy to work with from a paper and pencil point of view. But this is the functional form. It involves sigma here, sigma squared here, and mu here. And so basically, you can kind of see that when sigma is big, then it takes a further distance away from mu to get the same value in the exponent. So you can kind of see that why sigma is large, things start to spread out. When sigma is small, things are really peaked around the center. Now, of course, no matter what sigma and mu are, this whole thing has to integrate to 1, right? So we still need to have the properties of a probability density function, which are that the integral of the PDF, which in this case is, again, I'll just write it down to get used to it. Since this is a PDF, this has to be true. Now, let me just say that it's not so easy to prove this from a paper and pencil point of view. I can do it, but it's not really that constructive at this moment where I'm just trying to get you some intuition. So if you want, I'll come back and talk about that in a different lecture. This is the PDF. What is the, I should just say this is equal to 1 for being a PDF. What is the CDF? So the CDF is integrating up to some certain point the PDF. And again, it's this integral that has infinity at the bottom and some definite value at the top. Oops, sigma goes here, E goes here. So it's like we're integrating values up to x. Now, unfortunately, this is also not something that's very easy to evaluate by hand. And so oftentimes when you're doing Gaussian problems, you end up having to use numerical tools or tables. Maybe you remember from calculus that sometimes you had to compute these so-called Riemann sums, where you add up a bunch of rectangles if you want to approximate the area under some confusing function. That's one way to do it. MATLAB, Mathematica, Wolfram Alpha, all those places have these Gaussian integral tables kind of built into them. So you can use those when it comes to working problems. Let me think about what the CDF looks like, right? So again, the CDF should start at, now in this case, I should kind of be a little bit careful. Let's put mu out here. So I know that no matter what the value of sigma, since everything is symmetric, I have to reach the halfway accumulation point at mu, right? Now, if sigma is small, that means that not much is accumulated until I get close to mu, and then I kind of like shoot up, and then I kind of top out again at aggregating all the probability, right? Whereas so this is like sigma small. If sigma is large, then I may start accumulating probability earlier, and I may kind of tap out to the asymptote later, right? But this is kind of the intuition for what the CDF should look like. Now, the CDF depends on mu and sigma, right? And I can't have a table for every possible mu and sigma. So instead, what we do is we define what's called the standard normal, which you'll sometimes see called Z. And so this basically means it's a Gaussian with zero mean and unit sigma. Okay. So what is the CDF for that? The CDF for that, we're going to give a special symbol called phi, which is just the integral of the PDF for the standard normal. Sigma is equal to 1, mu is equal to 0. So things take a particularly easy form, right? And so this has, a bunch of tables. If you look in old math books, and again, now that everything is computerized, you can do this in MATLAB. And again, what does this represent? This represents the area under the Gaussian PDF when mu equals 0 up to some certain point x. So it's basically this value. Now, sometimes in engineering, when we want to know the answers to questions like, well, what's the probability that a part lasts longer than 50 years? That's more like looking at the area under the tail of the Gaussian, right? So this here is sometimes called Q of x, which is just 1 minus the CDF. And so it turns out that when you look in probability books, you're usually going to find tables of this Q because people are interested in how much energy or how much stuff is there left in the tail of this distribution. Okay, and then how do we use these tables? I'm going to do a whole lecture on that next, but let me just give you a preview to say, okay, what is the CDF of a generic Gaussian? So this is some Gaussian with generic mu and sigma. The CDF is defined as this probability, and what I could do is I'm just going to subtract the mean and divide by sigma on both sides. So nothing has changed here. Now this is a new random variable. This turns out to be Gaussian with zero mean and sigma equals 1, right? So this is actually just the phi function of this particular number, or 1 minus the q function of this particular number. Now I'm going to show you, I know this is a little bit abstract, we're going to do a whole bunch of examples in the next video where I'm going to use this kind of idea to solve problems involving generic Gaussian random variables. So I'll see you in that next lecture.